evacuated from Hurricane Rita. So Rita was the same year as Katrina, and it was also a very, I believe it was Cat 5 at one point. I don't remember all the details. When it was in the Gulf, and it was basically aimed right at Houston. And so they ordered evacuation, and it ended up being, gridlock on the roads, getting out of town, and I think 100 people died in the evacuation.
Yeah.
So since then, I think they've had a couple of storms and some more targeted evacuations for those like Ike, but they haven't really had any direct hit or any major damage. And then, like Andy said, they flood all the time, but not like this.
It's not even a direct hit on this time, right? It Corpus.
Right. But the forecasts were pretty clear with a bullseye of QPR or precip over that area. But
I'm just thinking like in the mind of the public, like, oh, the storm.
Oh yeah. No, I understand that. It's just gonna rain a lot, so unless I'm in some place that it flooded whenever last time we got foot of rain, that you just sort of go about business as usual. But this is, the forecasts that were coming out of the models are just so far off the chart. I've never seen anything like it, and I've been watching these models for a long time. So, you're in completely unprecedented territory. So, I don't really know, what you can say about the impacts ahead of time, and I think that's sort of where they were. They knew that the hurricane was going to hit them. So, the rest, the precip is too uncertain to really know for sure. So I think it's going to be discussed for a long time, but wow, just awful. So we got a big crowd today. It's good. Anybody have any questions before we get started? Let's see how the pen works. That looks all right. So we're sort of trying to go through a quick review of stats and some terminology and concepts, so we're all on the same page, and this stuff's always covered in your stat 301 or 350 or whatever you took. What that's worth, not that I'm saying anything bad about the stats class, but it's not something we use a lot, right? But here we're going to do statistics, and so I think it's important that we start here. So talking about hypothesis testing, and typically we're trying to make some inferences about the statistic that we're calculating, right? And there's different kinds of testing. We talked about that already. Parametric, we either know from theory or assume based on the type of data we're dealing with that there's a function that fits the sampling distribution. And this is the distribution for the statistic that we're interested in. So it's a little bit, this is a concept that I don't always get when I'm thinking of statistics. This isn't the distribution of the data, but of the statistic that you're computing from the data. So for example, we might have, I don't know, something like precipitation that has a very skewed distribution, but we're calculating the mean of that, say the annual mean or just some average. The distribution of the mean is going to look different than the distribution of the skewed data that we use to calculate that mean. So this, the other concept here is that we're usually dealing with a subset of the full true distribution of the data. We can only pull a sample of that. So it's a probability distribution. That describes how the sort of batch to batch variation of that statistic is going to look. So just, collecting some sample, calculating a statistic, presenting that number, that by itself isn't enough. In verification, we're trying to somehow measure the performance of the forecasts. We're always basing that on a limited data set, right? We haven't run the models forever. We haven't been forecasting for hundreds of years. We're just looking at, say, the last month's performance and just presenting that number without information of the uncertainty associated with it it's not enough information. So with this, the sort of typical way that hypothesis testing works in statistics, we first have to identify the statistic we're dealing with. Okay, that's sort of step 0. So this is something that we would compute based on the data that we've got in hand. And then, just probably more realistically, step 1, we define the null hypothesis. And this is usually denoted as H naught. And this is typically, it's sort of the opposite of what we're after. It's something that we want to reject and gives us a reference frame that we want to compare our statistic against. So one example might be that the correlation is 0, and we're expecting or wanting that statistic to be correlation that's a high number, right? We like to see correlations close to 1. Correlation of 0 means things are uncorrelated. So if you're looking at a correlation coefficient, that would be typical null hypothesis that you would use. Another one would be the difference in whatever stat we're looking at, the bias between the GFS and the ECMWF is 0. When we're really expecting to see some difference between those two, that one of those models better than the other, or at least significantly different from the other. So once you have this, there's usually a pretty obvious alternative hypothesis. And most of the time, it's just that H naught is not true. So sort of Boolean here, it's your null hypothesis, H naught is true, the alternative, not true. And then we need to obtain what's called the null distribution. And this is going to be that sampling distribution of this test statistic if the null hypothesis is true. Okay. All right, so that null distribution is the sampling distribution in the case null hypothesis is true. So this gives us something to compare our actual statistic that we compute against this. And we see that we're what part of this null distribution we're in. Okay, so that's the next step. Compare stat that we're calculating, the test statistic, against this. And if it happens to fall in a region of that null distribution that's unlikely, like a small probability, then we can reject that null hypothesis. Okay, so if this falls in an unlikely region, and that's sort of a subjective call, and H naught is rejected. The idea is that it's too unlikely that this null hypothesis is true based on the data and the sample and the sampling distribution and our statistic that we have in hand. Now, if it doesn't, okay, if it falls in a part of the stat distribution that's common, then we can't reject the null distribution. So we'd say that H naught is not rejected. Okay, so falls in sort of the ordinary or common part of the distribution, the null distribution is not rejected. Now, that's different from saying that it's true. So, this is part of this, that it's always been sort of difficult for me to grasp. It's sort of
not false.
True. Doesn't make it true. Yeah, Andy.
Our staff professor said fail to reject. It sort of like solidifies that concept. It's not saying it's true, but you just fail to say it's false.
Fail to say it's false. That's good. Yeah, that's good.
Not gonna have any of you in a courtroom.
So there's a couple ways you can kind of visualize a probability distribution, right? You can draw, a PDF, sort of like a continuous histogram, and a classic is the bell-shaped Gaussian. So let's say our null distribution sort of looks like that. I don't know, for whatever stat that we're looking at here. And again, this would be the distribution of that statistic that we would expect if the null is true. So whatever it happens to look like. We can also look at it as a continuous distribution function, which is basically the integral of this. And that looks more like an S-shaped curve. So this is basically telling you what's the probability that X is less than X, and this is what's the probability of X. So it's just a different way of looking at the same distribution. So if our test statistic is sort of out here and near the tails of the distribution, right, where the probabilities are low, then that's where we're rejecting that null hypothesis. So that's either, it could be on the low side, it could be on the high side. So in PDF space, it's sort of out on the limbs or the tails of the distribution. CDF, it's where things are getting very close to 0 or 1 and flattening out when you visualize it that way. And then this gets into topic of test levels or p-values. So let's say, go back to this example, our null distribution looks something like this. The test statistic comes out pretty far on the high end of that distribution. We can look at the area under the curve for that null distribution. For values of that statistic that's greater than or equal to our test statistic value. Okay, so let's say that this ends up being 5% of the total area under the curve, okay? So that is what we call the p-value or test level for that statistic. Now, the question of how far out is too far. What is the threshold that we use to make this determination? It's subjective. Okay, so how far out does this need to be for us to classify it as unlikely? So 5%, 1%, 0.1%. This is a subjective decision. So if we use, say, a 5% threshold, we're providing that specific value, this probability that we've got a range of values that starts with our test value and for things that are even more unlikely, that kind of range, that those things could occur. So let me write this down. This idea of a p-value is a specific probability that range of values that begin with the one we observe, which I've drawn with the line here, and then including all the possible values that are at least as unlikely as the one that we calculated from our sample. So that probability that these would occur if H naught is true. So there's a chance, right? There's a small chance that this null hypothesis could still be true, and we are observing values that are as unlikely as we got or worse. Okay, so you're saying there's a chance. That's what we're talking about here. And again, the sort of subjective choices made here, 1%, 5%, and we reject if that p-value is less than that subjective choice. So we'll call that the test level. And is not rejected otherwise. So it's that probability that, what we found or something even less favorable could have actually been observed by, some fluke, random chance, if the null hypothesis were true. Now I've just considered sort of that value of our sample statistic and say numbers that are higher as unfavorable. In this case, we call that a one-sided test. But we could also consider both tails of the distribution, two-sided tests. And that would be something we would apply if, say, we're dealing with a statistic that could easily be, say, positive or negative, and we're not really expecting that the values that will violate the null hypothesis will be on one side of that distribution or another. And so the two-sided test, we still report the value, the subjective test level ends up being our values, say 5%, but divided by 2. So we kind of split that into the two tails of the distribution. So now we're looking at 2.5%, 2.5% on either the high side or the low side of that null distribution. Okay. Now, related to this, are confidence intervals. And typically, sort of, we'll see this displayed visually. We'll have our sample value and then some bars that, again, will define some kind of level here, 95% confidence interval. On either side or about that sample. And it's a little bit different. And this, again, these are subtle distinctions here. So the idea here is that there's some either what's called population value of the statistic. And I'd like to think of, say, measuring or what's the average height of a human in 2017. And we can't measure everybody on the planet in order to figure out that statistic. So we take a batch, we take a small sample, measure everybody's height, average it, get a number. How close is that number going to be to the actual true value of the entire population? It depends, right? It depends on how that actual measurement varies across the entire planet. It depends on how many people we actually sample, our sample size. And so the confidence interval is trying to assess that, trying to say that there's a certain level of confidence that the value that we've calculated from our sample contains the population value, somewhere that true value is in this range. Okay, so population versus sample is where this comes into play. And say we are, this again gives us that sort of batch to batch variation in the statistic. So, again, if we pull the measure a different 30-person sample, calculated the mean, we would get a different number. So how would that vary from batch to batch? And if we did enough of those, we could come up with a distribution, and this gives us that sort of 95% of the area under that curve for that particular statistic and batch to batch variation. Okay, so this confidence interval I'll call CI. This gives us a specific level of confidence that the population value is found there, somewhere within that range, that interval. So this also gives us this CI, this range of other possible values of the sample statistic for which a hypothetical null hypothesis would not be rejected. So fail to reject. Try to remember that. That's a nice way to explain it. So for our purposes, you'll see some score that gets calculated, and confidence interval displayed around that score. And you might have test whatever measure of performance against some other model. And a lot of times we want to say something about the difference between the performance of these two systems, right? We want to be able to confidently say that the difference in that statistic has some significance to it. And so calculating the confidence interval based on that sample that's just from that one model on its own, and comparing it to the confidence interval that's calculated from the sample of the other system, people tend to then look at the overlaps between the confidence intervals. And if they overlap, they say, well, there's no significant difference between them. And that's not necessarily the case. Okay, so the overlaps can be deceiving. The more appropriate thing to do is to base your statistic on the difference between the two scores. Okay, so let's again just call this value S. And instead, we want to look at delta S. I don't know, let's say GFS minus ECMWF. We calculate the value of the sample and the confidence interval about that set of data and see, in this case, if the confidence interval includes 0. You will find instances where these, say, 95% confidence intervals overlap when you look at the two separately, but when you calculate the statistic based on the difference between the two, that 95% confidence interval actually does not contain 0. And that's really what we're after. We want to be able to see, is 0 a reasonable value where we would reject our null hypothesis. And the null hypothesis here would be that these two are the same. So I see this all the time, papers I review, and people will just look at the overlap of the CIs just based on the separate samples, and you really need to do that difference and look at the confidence interval of the differences. So we've haven't really defined this, but we've basically been talking about statistics based on scalar numbers, sort of single value. We can also do statistics based on vectors, multivariate statistics. Not sure how much we're going to do of that in this class, but we do a lot of this in atmospheric science. This is where we have vectors instead of scalars. And it's, do we have multiple numbers or one number? That's really what we're talking about here. So, an example would be multiple values, multiple variables at a single location, and then lots of those locations. How do we deal with those statistics? Another example would be, say we have a grid of temperatures over the United States. So we have lots and lots of values for a specific time, and then we want to look at lots of times and the statistics of how things covary within that spatial grid. So we can have multiple locations or a single variable over time. What we're really interested in is how these multiple numbers jointly behave, right? How do they interact, covary? There's usually some interesting things going on, either between locations or between variables, and the multivariate statistical methods allow us to tease that out. So the difference here is that we need to use matrix algebra, which means we're dealing with vectors and matrices instead of single numbers. So that notation, I think we'll use this a little bit in this class. And so an observation is denoted by a vector. So the vector, call x, and x contains multiple values, x1, x2, down to xk. Okay, so this is a column vector. It has k variables in this case. And a mathematical definition, you would say that x belongs to Rk. So it's real numbers, dimension k. And we could visualize x as a point in k-dimensional space. It's kind of hard to plot that, but if it's 2 or 3 dimensions, we could. Whatever, those different variables end up being different dimensions in that space. And so if we have lots of observations, then we collect those vectors, those column vectors, into lots of rows. Okay, so that ends up being a matrix. Okay, so a collection of observations, a matrix, or at least is denoted that way. And a lot of times that's called the data matrix. So often that's either a capital letters used or some kind of brackets to denote that. And we're basically going to have n of these column vectors that go into the large data matrix. So each of these are one of these. So sort of going from the most abstract way of denoting it, and we have a row of these n column, or we have n of these column vectors, and that ends up looking like this. Where we have so I've just kind of blown up all of these column vectors into their individual elements, and that gives us the whole data matrix. And so now a particular element would be denoted as xij. Well, the first number is the row, the second number is the column. So that kind of lets you know where you're at in the data matrix. This matrix now has a dimension, so we write it mathematically like this. It belongs to a set of reals with a k by n dimension. That means we have k rows and n columns. So the multivariate statistical methods, basically just different ways of dealing with these data matrices. And we'll talk about this a bit in this class, but it's usually a lot more depth in other courses. Very fascinating stuff we can do with these multiple variables and the data matrices. So I better stop there unless you have any questions. Yes, sir.
For confidence intervals versus hypothesis testing, to me, it seems like the confidence intervals implicitly display a lot more information as opposed to like going through the steps and then writing it out. We rejected or failed to reject the null hypothesis.
Yeah.
It seems like the confidence interval lays out a lot more information and pictures worth 1,000 words. Is there a downside to that? Like,
I think you're right. I I'm sure someone that's steeped in statistical theory would, be able to come up with some case where you would benefit from just doing the hypothesis test. But I think you're right. You do get that nice display of the information related to the uncertainty, and I think that's almost always what I see
that was my second
and verification is confidence intervals. Everyone's going to ask for them if you don't supply them.
Okay. That was my follow-up question.
Yeah. So I definitely agree with you there. Mainly just wanted to refresh everybody on this stuff. Yeah, that's a good point. Okay.